I deposited money in the bank, a financial institution. I sat on the riverbank, the edge of a river, same 5 letters, opposite meanings. No dictionary entry tells the model which one you mean. The word bank is identical in both. So how does it know? It lets the word bank look at its neighbors, money in one sentence, river in the other, and absorb their meaning. That looking at neighbors mechanism has a name, attention. It's the engine of every modern language model, and today we take it completely apart. Here's the one-sentence version. Attention lets every word look at every other word in the sentence and absorb context from them. So the same word bank comes out as a different vector depending on the words around it. Its meaning is computed on the fly, not looked up. And it does this through 3 roles every word plays at the same time: query, key, and value. By the end, you'll know exactly what each one does. Let's see it. Here's sentence 1, with bank as the word doing the looking. Attention draws a connection from bank to every other word and gives each connection a weight, drawn here as line thickness. In this sentence, the thick lines go to deposited and money. Bank attends most to those, so its meaning shifts toward finance. Now sentence 2, I sat on the riverbank. Same word, but now the heavy attention lands on river and sat, so bank shifts toward land and water. Same word, different neighbors, different meaning. That dynamic reweighting is the whole idea of attention. Now let's open it up. Here's the plan. First, query, key, and value, the 3 roles, with an analogy that makes them obvious. Second, the 4-step attention math score, scale, softmax, weighted sum. And we'll do it with real numbers, as always. Third, a trace along. We'll watch bank literally become a finance-flavored vector, step by step. And a bonus after the cheat sheet, how models mask the future during generation, plus the attention heat map that visualizes the whole thing. Heads up, this video ties the whole series together. Dot products from the vectors video, the weight matrices from the matrices video, and Softmax from the Softmax video all show up here. The core idea, stated plainly, every word builds a new version of itself by mixing in the words it finds relevant. And relevant is not hard-coded. It's computed fresh for every word in every sentence, which is why the same word behaves differently in different contexts. Each neighbor gets a weight, some high, most low, and because we'll use Softmax, those weights always sum to 1. It's a weighted blend. So bank surrounded by money literally ends up as a different vector than bank surrounded by river. Context gets baked right into the numbers. Query, key, and value sound abstract, so picture a library search. The query is a sticky note of what you're looking for. For bank, something like, I need money-related context. The key is the label on each book's spine, what that book is about. Every other word in the sentence has one. And the value is the actual contents inside the book, the information you take away if you opened it. The search works in 2 moves. First, match your query against every key. That gives a relevant score for each word. Then take a weighted blend of the values, mostly from the books whose keys matched your query best. That blend is the word's new context-aware vector. So where do words query, key, and value actually come from? This is the payoff to the matrices video. You take the word's embedding vector and multiply it by 3 separate learned weight matrices. And a weight matrix, remember, is just a learned grid of numbers. Multiply the embedding by W-q, and you get its query vector. Multiply the same embedding by W-k, and you get its key. Multiply by W-v, and you get its value. 3 matrix multiplications turn one word into its query, key, and value. And remember, those 3 matrices were learned during training. That's what the model actually learns: how to ask, how to advertise, and what to share. Step 1, scoring. We take bank's query vector, let's say 2, 0, and dot it with every word's key. Straight out of the vectors video, the dot product measures how aligned 2 vectors are. Query.money's key 2, 0, 2 times 2 plus 0 is 4. High, they point the same way. Query.deposited's key 1, 1, that's 2. Moderate, query.the key 0, 1, 0. Orthogonal the is irrelevant to this query. So the raw attention scores are 4, 2, 0. A high dot product just means this word's key answers my query. This is literally the vectors video doing attention's job. This next step is quick, but it quietly keeps the whole thing stable. Step 2, scale. Before we do anything else, divide every score by the square root of dk, the dimension of the key vectors. Here our keys are two-dimensional, so dk is 2 and the square root is about 1.41. Our scores 4, 2, 0 become 2.8, 1.40. Why bother? In a real model, dk is 64 or more, and the dot products can get enormous. Feed enormous numbers into Softmax and it saturates, one word grabs essentially all the attention, and learning stalls. Dividing by root take keeps the scores in a sane range so the Softmax stays smooth and the gradients stay healthy. It's a stabilizer, nothing more, but it matters. Step 3, Softmax. And yes, this is exactly the Softmax video. We turn those scaled scores into a clean set of weights that sum to 1. Exponentiate. E to the 2.8 is about 16.4, e to the 1.4 about 4.1, e to the 0 is 1. The sum is about 21.5. Divide through and you get the weights: money 0.76, deposited 0.19, the 0.05. These are the attention weights. They tell us bank is going to be built from 76% money, 19% deposited, and a sliver of the. Softmax turned raw similarity into a recipe. Step 4, the payoff. We take each word's value vector and blend them, weighted by the attention weights we just computed. 76% of money's value, 1.4, gives 0.76, 3.04. 19% of deposited's value, 2.3, gives 0.38, 0.57. 5% of the fees value, which is basically 0, contributes nothing. Add them up, 1.14, 3.61. That is bank, brand new, context-aware vector. Bank walked in as a generic embedding and walked out pulled hard toward money's direction, that big second number. The model now represents this bank as a finance bank. That's attention end to end. Here it is, the famous attention formula, the one at the heart of the transformer paper. Attention of QKV equals softmax of QK transpose over root DK transpose over root DK times V. And you've earned every symbol. QK transpose is step 1, every query dotted with every key. Dividing by root DK is step 2, the scale. Softmax is step 3, the weights. And multiplying by V is step 4, the weight sum of values. That's one line of math you have now done, in full, entirely by hand. The intimidating formula was always just 4 friendly steps: score, scale, softmax, blend. Here's why this is such a big deal. In our sentence, bank came out as 1.14, 3.61 the finance direction. Run the very same word through I sat on the riverbank, and now river wins the attention. The values blend differently, and bank comes out as something like 3.2, 0.9, the land and water direction. Same starting embedding, same word, but different neighbors won the attention, so the output vector is different, which means no word has a fixed meaning anymore. Its meaning is negotiated with its sentence every single time. That's what makes transformers understand language instead of just matching keywords. Let's bust the big myth. Because it's called attention, people imagine the model consciously focusing, even understanding, the way a person reads. The reality is humbler and far more elegant. Attention is a weighted average. Each word's new vector is just a blend of the other word's value vectors, weighted by how well their keys match the query. There's no spotlight and no comprehension in there. Only a very fast question, asked in parallel for every word. Which vectors point my way, and how much of each should I mix in? That's it. Quick one for the comments before we go further. What's a sentence where one word's meaning completely flips depending on the words around it? Bank, bat, lead, left. Drop your favorite ambiguous word below. I'll pin the best ones, and they're exactly the cases attention was built to handle. You now know the full mechanism. Here's the one upgrade real models bolt on top. Multi-head attention. A single set of QKV can only capture one kind of relationship at a time. So real models don't run one attention, they run many in parallel, called heads. Each head gets its own W-q, W-key, and W-v, so each one learns to look for a different pattern. One head might track which words sit nearby. Another might link subjects to their verbs. Another might connect a pronoun like it back to the noun it refers to. Different heads, different jobs. They all run at the same time, their outputs get concatenated, and one final matrix, WO, from the matrices video, mixes them back together. A GPT-style model uses dozens of heads in every layer, dozens of simultaneous viewpoints on the same sentence. That's where a lot of the richness comes from. Let's put all 4 steps together in one trace for bank in money in the bank. First, multiply bank's embedding by W-q, W-k, W-v to get its query to 0, and do the same for every word to get all the keys and values. Step 1, score, query dotted with each key gives money 4, deposited to the 0. Step 2, scale, divide by root 2 to get 2.8, 1.4, 0. Step 3, Softmax, that becomes weights. Money 0.76, deposited 0.19, the 0.05. Step 4, blend the values by those weights, and bank comes out as 1.14, 3.61. Bank is now a finance vector, and crucially, this exact computation runs for every word in the sentence, in every layer, all at once. Score, scale, softmax, blend burn those 4 words in. That's attention for every token. Pause and screenshot the whole video on one screen. The pipeline, q.k transpose, divide by root dk, softmax, times v, out comes a context vector. Query is what I want, key is what I offer, value is what I give. Score is the qk dot product, scale is dividing by root dk, the weights are a softmax, the output is the weighted sum of values. Multi-head means many of these running in parallel, each with its own q, k, and v, then concatenated. And the one big idea, a word's meaning is a weighted blend of its neighbors, computed fresh every time. Bonus round, unlocked. Here's something the basic picture leaves out. When a model is generating text, its whole job is to predict the next word, so it must not be allowed to peek at words it hasn't written yet. Say it's working at the word the in money in the bank. It's allowed to attend to everything up to and including the money in the words already on the page. But if it could attend to bank, the word still in the future, it would be cheating, because that's exactly the word it's trying to predict next. The fix is the causal mask. Before the softmax, you set every future word's score to negative infinity. After softmax, e to the minus infinity is 0, so those future words get exactly 0 attention weight. The result, every word can only ever blend in words to its left. That single trick is what turns attention into a left to right text generator. And notice, it's the same 4-step math we already learned. We just black out the upper right triangle of the score grid first, which is a perfect segue to seeing that grid. And here's the picture that ties it all together, the attention heat map. Every word is a row, attending to every word as a column. The brighter the cell, the more attention. Look along any row and the weights sum to 1. That's a single word's entire attention budget, divided up among the others. See the empty upper right triangle? That's the causal mask we just built. Every one of those future cells is 0, no word is allowed to look ahead. And the bottom row, bank, lights up brightest on money. That's the exact 76% weight we computed by hand. The other cells just fill out the fuller sentence. This heat map is the real tool. It's what researchers actually stare at to figure out what each head in a model has learned to do. Let's lock it in. 1. Attention is a weighted blend by similarity score with Q.K, scale, Softmax, then sum the values. 4 steps, nothing more. 2. It makes meaning dynamic. A word's vector is negotiated with its sentence. Every time, there's no fixed dictionary entry anymore. 3. This is the transformer's engine. Run it multi-headed, mask the future, stack it about 80 times, and you have the architecture behind every modern language model. And then what? Banks' new vector doesn't stop here. It flows into a feed-forward network, more matrices from the matrices video, then up to the next layer, about 80 times over until a final unembedding and a softmax pick the next word, just like the softmax video. Attention is one powerful stage inside that bigger loop. And notice what just happened across the whole stack. Products from the vectors video, matrices from the matrices video, and softmax from the softmax video all came together right here in attention. This was the convergence point. You just learned attention, genuinely the hardest and most important idea in the series. Next up, embeddings and positional encoding. Here's the puzzle it solves. Attention looks at all the words at once, in parallel, so how does it know their order? How does it tell dog bites man from man bites dog? This is video 4 of 7. Drop your favorite context flipping word in the comments, and I'll see you in the next one, embeddings and positional encoding.